Okay, so we have seen the Black-Scholes formula in our slides. So here is the formula. So we can write a user-defined function to calculate the Black-Scholes call option price or the put option price. And you can see that we have our MATLAB function. This is just an example code. And actually, if you have the toolbox for financial derivatives pricing, then there exists the built-in function in MATLAB. So actually MATLAB already has the Black-Scholes formula for you. So you can see the BLS price. So this is under the financial toolbox, and you can see the syntax is given. So you can call this built-in function with the current price of the underlying stock, the strike price, the risk-free rate, time to maturity, and the volatility. So if we input these, we can obtain the European call and put option prices. But if you don't have the toolbox, then you need to write your own function. And again, that's not very complicated. We can simply follow the theoretical formula given here. And notice that these n values, these are the cumulative distribution function of the standard normal evaluated at this D1 and D2 values. So first you can actually calculate D1 and D2, and then you can evaluate the normal CDF function, as you can notice here. And basically, finally, I use the put and call parity to calculate also the put option price. So here's my MATLAB user-defined function for this, and we can also test our function on our workspace. For example, we can go and input some example values. Let's say volatility is 30%, and suppose we have half year to maturity, 3% as the risk-free rate, and let's say the strike price is 52. So you can see that we get the Black-Scholes price, and we can also verify whether our function returned the correct values. We can use the Black-Scholes price, the built-in function in MATLAB, so we can enter the same numbers. Okay, so the strike price is 52, so we have 0.03, and then we have 0.5, 0.3. So we can see that actually we get the same call option price, so the formula is verified. Our function is working properly. Also, you can use your Black-Scholes pricing function to see how does the option prices behave under different scenarios. For example, you can consider a variety of strike prices defined by this grid from 20 to 150. So in this case, our underlying stock price currently is supposed to be 100. The strike price is 100, but we are considering now a vector of different strike prices. And then we can create some plot in MATLAB to analyze or to understand how does the call option price changes with respect to changes in the strike price or the underlying stock price, time to maturity, or the volatility of the stock. Okay, so all these can be done, and you can easily generate different type of plots. And also notice that in our user-defined Black-Scholes pricing formula here, it is okay to input a vector of, let's say, volatility, or we can enter a vector of different strike prices, because these operations, if you pay attention, we are using this dot, which makes these operations as a vector term-by-term operation. So it is general enough to accept a vector of inputs for the different variables of choice that you want to analyze. So basically we can create these figures, and next we will see how to use the Newton's method or the bisection method to find the implied volatility of the option.